Hello, class. This is complex analysis for March 9th. Let's get started. I wanted to first recap the theorem that we proved last time on Friday. If we have if we have a power series with positive radius of convergence, then we show that it has a derivative, so it's analytic. And we also showed that at the same time that the formula for derivative is what we kind of expect. We use the power rule inside of the power series, and that basically gives you the derivative, the power series formula for the derivative itself. I wanted to say a couple words about the consequence of this. Of course, if you can do this for one derivative, you could do this for many derivatives. So this is the general formula that we'll get. If we plug in z naught into the z in the formula, we'll just pick up the constant term. And on the nth derivative, if you plug in z naught, we get the constant term is going to be n factorial, this n factorial coming from the power rule. And that's the original nth constant coefficient for the power series. If you kind of flip this around, you can rewrite the nth constant, nth coefficient to be nth derivative evaluated at z naught divided by n factorial. Now notice that this depends on the function itself. The formula is kind of written out. What I mean by that is that this constant has to be unique, right? If I give you the function, the nth derivative of z naught is already given to us, right? So this is what the nth coefficient has to be. If you have two different power series with different coefficient, then it has to be a different analytic function. So all these coefficients has to be unique. Okay. All right. So we've shown that power series would have to be an analytic function. What we'll talk about in this lecture is that this could go the other way as well. If you have an analytic function, then it could be written as a power series. That's what we'll try to prove. Okay, so this is the more precise statement. So if you have an analytic function on some ball of radius big R centered at z naught, then the function could be written as this power series inside the entire ball, with ak being the kth derivative divided by k factorial. This is the same thing as this integral by the generalized Cauchy integration formula. The reason why I've written it out as an integral formula here is because in the proof, that's what we use, but it's also equivalent to this formula over here. All right, let's look at the proof. All right, so we pick any z inside of the ball, and so let's make this. I want to pick this little r that's less than the big R. That's the radius of the convergence. This R is the radius of the domain. Z minus z naught is the distance from z to the center of the ball. And I want to pick the little r so that it's between those two numbers. Okay, that's the radius where we're going to integrate counterclockwise. Okay, so here's Cauchy integration formula. We know that this is true. This formula has to be true. But note that we're integrating around the pole at z. And if you look at the formula for the coefficients, I want this to have the pole at z naught instead, right? Instead of z. So this is not z naught. So what we could do is we can kind of squeeze that z naught in. So we're going to add and subtract z naught so that we have this formula right here. And then from here, I'm going to, by the way, I'm using a new Greek letter here. This is a Greek zeta. It looks like a squiggly, it's a little bit hard to draw. Anyways, I have these four terms here. What I'm going to do here is I'm going to factor from the bottom zeta minus z naught. So if I factor that out, I'll get a 1 here from these two terms. And the other two terms does not have zeta minus z naught in it. So when I factor it out, I'm going to have to make up for it by dividing it. So this is an awkward way to still write f of z. Okay. So I'm going to try to rewrite this right here. So this is really awkward to write over and over. So let me just call that w. So w is z minus z naught divided by zeta minus z naught. Okay. We know from the formula, partial sum formula that we have for geometric series, that if I add up 1 plus all the powers of w up to n minus 1, then this is the formula for the partial sum. If I take this negative w to the nth over 1 minus w on the left-hand side and add it to bring it to the right-hand side, that's what we have here. So 1 over 1 minus w, that's this part. I'm going to rewrite this as sum of these powers. All right, so the next line is going to be super ugly. All right, so note that the first term should be 1, but I do also have one factor of zeta minus z naught. So it's 1 divided by zeta minus z naught. And on subsequent terms, I have different powers of w's, but I also multiply back in zeta minus z naught. So it has, the denominator has 1 higher power than the numerator. That's why we get this. And this will continue on until w to the n minus 1 term right here. That's that. And the nth term. So this looks slightly different from this. Let me try to explain it. So w to the nth power is this bit right here. I do have to multiply by zeta minus z naught. So there's 1 extra factor of zeta minus z naught. And we also have 1 minus w here. So this is what should come right here. But I just wrote that as zeta minus z. Well, that's because this denominator is same thing as zeta minus z. We did some algebra gymnastics to rewrite zeta minus z into this weird form. So I'm gonna go back and rewrite it as zeta minus z here. So that's why we have this here. And this is equivalent to this denominator over here. Okay, so most of these terms inside of this integral corresponds to the generalized Cauchy integral formula. So the first term will give the first coefficient for the function. for the power series version of the function. This is a power 2, so this is the first derivative of the function f evaluated at z naught. So that's c1. And then z minus z naught on the top is still written out here. So this is the power series up until the n minus first term, except the nth term is different, right? So I'm just gonna call that Rn of z. And what we're going to do is that basically what we have is that f of z is equal to this power series. And this is the partial sum of the power series. I could get this, that the power series converges, if I can show that this thing goes to 0 as n goes to infinity. So how we're going to do this is by the ML estimate. So let's look at the modulus of Rn of z. This is going to be less than or equal to 1 over 2 pi. The I is missing because we're looking at the modulus. In the inside, we have f of zeta here. So f of zeta, I'm just going to look at the modulus. And then I'm going to look at this part of the term, z minus z naught over zeta minus z naught to the nth power. So that's written right here. Oops. And 1 over zeta minus z, I've written right here. And we're also looking at the length of this integral. Okay. So f is analytic in this circle C. So it's continuous, right? If it's a continuous function on a compact set, it is bounded by some positive number m. So this part has to be bounded. This second factor here, zeta minus z naught. Remember, zeta is running across this curve C. That's the circular path of radius little r. So the denominator I could just rewrite as the modulus of this guy is always equal to little r. So that's what we have in the denominator. 1 over zeta minus z, the closest that this zeta gets to z is this distance right here. R is how far away that zeta is from z naught. And using the opposite direction of triangle inequality, this is the smallest that this thing can get in the denominator, which will make this the largest it could be, because a smaller denominator means bigger overall. Okay. All right, and the length of this circular path is going to be 2 pi r, so 2 pi little r. So the 2 pi in the front will cancel out, and I have an extra factor of r here because of the r we get from the circumference. And we look at this expression. As n goes to infinity, the only thing that's changing is this factor right here. Note that the distance from z to z naught is less than the distance r. So this is getting smaller and smaller as n goes to infinity. So these terms are going to 0. This thing does converge. Okay, so we get that the power series converges with radius at least big R. I didn't show that it diverges for bigger than R, but I did show that if Z was closer than big R, then it has to converge. So there we go. We get the converse. Okay. So uh, one bonus that we get from proving this converse, so what we proved was that if we have an analytic function, it could be written as a power series. But we got a little bit more than that. We got that it's a power series and the radius is at least big as the original domain that's given to us. Here we go. So if f is analytic and ball of radius r, then this power series converges for the entire thing. But these coefficients right here does not depend on the original radius r, big R. So if it was possible to be extended to an analytic function beyond this, if it could be extended to bigger ball, then it will converge for that bigger radius as well. The point is that this f converges for the largest possible radius of convergence possible. You can tell that I'm excited about this statement because I underlined for the first time and there's a couple of exclamation marks right there. So here's how you should think about it. So let's say this is some domain D for a function that we're looking at, and Z naught is right here. We get the largest radius there, but if it's actually possible that this domain could be extended, then you might actually converge for a larger circle. So you might actually discover that this function could be extended in a portion that you didn't know it could be extended before. Okay. All right, so I want to talk about a couple of the consequences. Let's look at the function e to the z, the exponential function. The derivative is all e to the z because derivative of e to the z is e to the z. If I evaluate all the derivative at 0, it's going to be e to the 0 is 1 for all derivatives. So this would be the power series based at 0 for this analytic function e to the z. E to the z is an entire function. So the largest possible radius that we could give is infinite. So this power series is convergent everywhere. We get that for free. And we could do the same thing for cosine and sine. If you take derivatives and then plug in 0, we'll get all the terms with the sine of 0 is going to be 0. And cosine terms will be alternating. Cosine of 0 is 1. And negative cosine of 0 is -1, so it'll alternate signs otherwise. So all the even terms are left over with alternating signs. That's the power series for cosine, and something similar for power series of sine. Both of these are entire functions, so radius of convergence have to be infinite. Let's look at a case where the radius is not infinite. So this is the principal branch of the logarithm function. The first derivative is 1 over z. The next derivative is negative over 1 over z squared. And then the next derivative is 2 over z cubed, negative 3 factorial over z to the 4th, and so on. Maybe you could get the pattern from there. The kth derivative is going to be alternating signs, and we have k minus 1 factorial divided by z to the k. So the factorial on the top is trailing 1 behind the power of z at the bottom. We can't plug in 0 for this. It's not defined there. So let's base our power series at 0.1. So if I plug in 1, this is what I get for the kth derivative, right? So if we take this and divide by k factorial, we'll get the coefficients of the power series. Here we go. So k minus 1 factorial divided by k factorial will just give us k in the denominator. So this is going to be the power series for the log function. We're basing it at 0.1. There is the function is not defined at 0. So the largest possible radius this could converge is exactly radius 1. And that's what we get here. Okay, so I think this is important. So I think it's worth restating what we got out of this. So if we have an analytic function in domain D, and you look at any point inside of that domain, and you can rewrite that analytic function as a power series using this formula. For any z within the largest possible radius r disk that you could fit inside of the domain. And another name for this is Taylor series. You probably remember that from Calc 3. Okay, so we get that power series are analytic functions. And if you have an analytic function, it could be represented by power series. That's the main result for the day. But let me give you some new technique that arise from this. So let's see if I can draw something. Okay, so let's say this is a complex plane and we're basing at z naught. And let's say I know that the function has a pole there. So at this point, this is the largest radius of convergence over here. But I want to know what the function is behaving like over here. Let's call this point z1. What I could do here is I could draw some kind of continuous path connecting z0 and z1. And everywhere along the path towards z1, I could compute different power series along the way. So if I start here, I can go over here, and before I exit the original disk where this power series is defined, I look at the values and derivatives here and create new power series based at this new point. Then the power series is going to agree on the overlap. And because it converges for the largest radius possible, I could go a little further along my path. And before I exit, I can look at the values and the derivatives there to compute new power series that converges for this circle. And it agrees on the overlap. And I can go a little bit further. Before I exit the circle, I get another power series until I could get to that Z1. That's the place that I was interested in. So I can kind of string along different power series with different radius of convergence to kind of extend the domain of the analytic function to explore the value of the power series over there. Does that make sense? So we can kind of take our disk along with us as we explore the function, and we are able to discover how the function is behaving later on in the path. This is an extremely powerful technique. It's awesome. It does come with a warning though. So here's a warning. Okay, let's say we have a pole here. And here's my Z naught. Here's my path. Here's my Z1. And let's say I want to do this analytic continuation along this path. So this is a pole. So let's say I have radius of convergence there. So I go over here. I have this convergence. Oops, I have to do there. I'm going to make series of disks up until I get to Z1, let's say. So as the function travels all around, every time I go from here to the next spot where I compute my next power series, the overlap has to agree with the original function. But as it continues, if the path comes back around a pole and I get a power series that converge here, this power series does not have to be related to the original power series that we started with. So in the overlap here, the function do not have to agree. Might not agree with overlap at the end. So for example, let's see, can I extend another page here? No. Let me erase something. Okay, sorry about this mess. Okay. For example, you could do this technique for the log function. We usually deal with the slip plane, but if you're using analytic continuation, you don't have to make slits, right? So, but if I go around and come back, anywhere along the path, the overlap to the next step has to agree because it has to be continuous on the overlap. But by the time it comes back around, the function value here and function value here, these two power series will not agree on the overlap. In fact, we know exactly how much they're off by. The imaginary part will be off by 2 pi I, right? Because that's what log function does as it goes around. So we have to keep that in mind when we use analytic continuation. Anyways, that's it for today. If you have any questions, record the timestamp and post it on the course discussion board or the course Canvas page, and I'll try to answer any of your questions the best I can. All right, I'll see you guys Wednesday.